Hello, everybody. I'm here to talk to you today about Kirchhoffs laws. And Gustav Kirchhoff was a German physicist who made some contributions in spectrum analysis and optics and electricity. And two of the rules of electric circuits are named for him, and we call them, the first one we call Kirchhoff's current law, and the second one we call Kirchhoff's voltage law. And these rules provide a foundation for the analysis of electric circuits. So let's take a look at Kirchhoff's current law. This basically states that the amount of charge in a junction or a node where several wires connect, they must be equal to the amount of charge leaving the junction over the same amount of time. And because charge over a certain amount of time is electric current, this simply means that this law states that current in must equal current out. That's current into the node must equal current out of the node. Okay, so let's take a look at an example. And you can see here that we have three wires coming together at a point, and this point is called a node. Let's say that some electric current is flowing into that node from one of the wire branches. We'll say that it's 3 amps. All right, this means that every second, 3 coulombs of charge is entering the node from that wire branch. We'll also suppose that 4 amps is entering the node from the branch on the lower left. So what is the current leaving the node by the branch on the right? Right here. We'll call this I3. Because Kirchhoff's current law says whatever total current goes into a node must also come out of it, let's make a chart to organize this information. In one column, we'll organize the current going into the node, and in the other column, the current going out. We can see here we have 2 currents going into the node, and those would be I1 with 3 amps and I2 with 4 amps. They combine to make a total of 7 amps. There's only one possibility for the out current, that's I3, and this must be 7 amps also, because the in must equal the out. Let's look at another example that's in a circuit. This is a circuit with a voltage source and 2 resistors. You can identify these using the symbols in the electricity section of page 4 of the reference tables. All right, let's make some theoretical currents that are going through the wires of this circuit. So, here we go. Remember that the location where these wires are connected or branch off is called a node. That's where the node is. Let's make the organizational chart again. Okay. This time we have a labeled current going in with I1 with 9 amps. And we have a labeled current going out, I2 with 4 amps. The total in amps is 9. And the total out is 4. And these do not equal each other. So to make them equal, we add 5 amps to the outside. And the only way to do this is if we designate I3 as being 5 amps. Now the out equals the in. Okay. Now it's your turn to try. Pause this video and attempt to figure out the value of the current I5 and the direction that it's going, either in or out. Okay, go ahead and pause the video and try it. Yep, I really mean it. Try it out. Okay, I hope that you have now paused the video and attempted the problem. Right? Okay, let's set up our organizational chart and enter the known values. Okay. One thing that is interesting to note is that the node we're analyzing is a bit bigger. This whole area is the node. It doesn't come to a single point, but it still does have current going in and current going out. So the total current in is 13 amps, right? Well, the total current out right now is 4 amps. And these obviously do not equal each other. So that must mean we increase the outward current by 9 amps, and we can do that as designating I5 as being that 9 amp current. And now the in does equal the out. Finally, let's designate the direction on the diagram with an arrow and show that it's going outward. So that, in a nutshell, is Kirchhoff's current law. See you in the next video. Bye-bye.